Good morning. I'm Zach,
And I'm Emma.
and today we're going to be presenting the Gemini Planet Imager. We chose to present this topic because everyone uses instruments to study space phenomenons, but no one studies the actual instruments themselves. In the vast expanse of the cosmos, the exploration of distant worlds has captivated humanity's imagination for centuries. From ancient astronomers like Kepler and Galileo to modern day astronomers, uncovering the mysteries of our universe contributes to drive scientific innovation. Among the myriad tools at our disposal, GPI or Gemini Planet Imager stands as a beacon of innovation, uh, offering unparalleled insights into the celestial bodies that dot our night sky. Developed as a state-of-the-art instrument in 2013 and nestled in the Gemini South Telescope atop Cerro Panchon in Chile, GPI represents a significant leap forward in our ability to directly see and study exoplanets, which are planets that orbit stars outside of our solar system. Now that we know what GPI is, we have to know how it's made. GPI has 5 major subsystems. The first subsystem is the um, adaptive optics system, which aims to correct wavefront errors that may arise from atmospheres or GPI's own optics. The second system is the coronagraph system. The coronagraph system aims to mask diffraction of coherent starlight. And one of the specific coronagraphs in this instrument is the apodized pupil lyot coronagraph. The third system is the calibration or cal interferometer, which is a post-coronagraph wavefront sensor. The next system, the fourth one, is the cryogenic integral field spectrograph, or IFS. The IFS provides high spectral resolution and is paramount to GPI as it allows it to distinguish between different wavelengths of light with great precision. The fifth and final system is the optomechanical superstructure, or OMSS. The OMSS is a structural foundation for the rest of the components of the Planet Imager. A newer software is currently being developed and is expected to launch in late 2024 to early 2025, and is expected to render GPI 2.0 more streamlined, autonomous, and lower maintenance.
And the Gemini Planet Imager is unique in its method of identifying exoplanets. The device takes a picture of the exoplanet directly, unlike other devices, which I will talk about later. It does this by blocking out light emitted by the star it is orbiting in order to make the exoplanet more visible. This is possible because the GPI's adaptive optics sharpen the image of the target star by canceling out the distortion caused by the Earth's atmosphere. It then blocks the bright image of the star with a device called a coronagraph, which Zach just talked about, revealing the exoplanet. For example, we can see some pictures here of exoplanets 51 Eridani and 51 Eridani b, which were discovered in 2015 as seen from the GPI. GPI collects data about exoplanets, which includes their atmospheric properties, composition, mass, size, temperature, orbital periods, and even potential habitability. With the data collected using GPI, planetary atmosphere and evolution models can be used to further estimate properties of the planet. For example, GPI helped to find that 51 Eridani b has a methane absorption that is comparable to that of Jupiter, which we can see here, which helped us classify it as a gas giant. Furthermore, it was found that 51 Eridani b has a temperature of 750 Kelvin, and its radius was estimated to be 1.19 times that of Jupiter. Although the Gemini Planet Imager isn't the only exoplanet observer to exist. The European Southern Observatory, or the ESO, and NASA have both created their own devices in 2003 and 2009, respectively. The ESO created the High Accuracy Radial Velocity Planet Searcher, or HARPS for short. We can see an image in the top right. HARPS is a spectrograph which measures the radial velocity of an exoplanet, allowing us to determine its approximate mass. HARPS has found hundreds of exoplanets using this method. The Kepler satellite is another apparatus created with the goal of detecting exoplanets. Built by NASA, the Kepler satellite was launched on March 6, 2009. In order to detect planets, it observes dips in the brightness of a star, which are caused by a planet crossing in front of it. Before the Kepler satellite ran out of fuel, it discovered more than 2,600 exoplanets, some of which may even have liquid water on its surface due to its distance from the sun. What makes the GPI special is that it allows us to take an image of the planet itself, and it can also pick out a planet from the star's glare and then use spectroscopy to measure the planet's size, temperature, gravity, and composition of its atmosphere.
To conclude, the Gemini Planet Imager has been a great addition to science, discovering numerous exoplanets and contributing information about its properties. This device has provided researchers with insight into the origin and evolution of planetary bodies throughout the cosmos. The future of GPI is hard to predict, although in 2022, it was revealed that the GPI was upgraded by the University of Notre Dame and the University of California, San Diego, into a device called the GPI 2.0. Its technology was evolved to improve its performance on stars and exoplanets. They are listed as an EMCCD-based a pyramid wavefront sensor, broadband low spectral resolution prisms, a redesigned apodized pupil lyode coronagraph, and a new instrument calibration unit with a new generation self-coherent camera. The first flight of this instrument, again, is expected to be seen between late 2024 and early 2025. Thank you.
Thank you.